A gas pipeline NPS 18 with 0.375 inch wall thickness transport natural gas specific gravity 0.6 at a flow rate of 160 million standard cubic feet per day at an inlet temperature of 60 degrees Fahrenheit. Assuming isothermal flow, calculate the velocity of the gas at the inlet and outlet of the pipe if the inlet pressure is 1200 psig and the outlet pressure is 700 psig. The base pressure and the base temperature as 14.7 psia and 60 degrees Fahrenheit respectively. Assuming the compressibility factor Z is equal to 0.95, what is the pipe length for this pressure if elevations are neglected? So now let's begin. Now we'll start with what was given. Now be given data. Now we are given the outer diameter to be 18 inches. Now we are also given the wall thickness to be 0.375 inches. Now we are also given the, the gas gravity G to be 0.6. We are also given the flow rate to be 160 times raised to the power 6 standard cubic feet per day. Now we're given this, then we are also given the inlet temperature, and since it is an isothermal, process. So that means T1 is equal to T2 equal to the gas temperature, which is 60 degrees Fahrenheit. So we have to convert this to Rankine, which is 60 plus 460, which will give us 520 degree Rankine, because we are supposed to use absolute temperature and absolute pressure. Now we are asked to find, okay, let me just write all that was given. We are given the pressure P1 to be 1200 psig. We are also given the outlet pressure or the downstream pressure, which is 700 psig. So this upstream and downstream pressure or inlet and outlet pressure. So now we are also given the base pressure to be 14.7 psig. That is to say the standard condition. Then the base temperature to be 60 degrees Fahrenheit, which is the same thing as 520 degree Rankine. Now, having given this, we now need to find the velocity, that is the inlet velocity of the gas, and the outlet velocity of the gas. So we need to look for these two things. So now, for us to do that, first we need to now introduce what we now need to use mass conservative, that is law of conservation. Mass is constant provided there is no gas that's charged in or no gas was ejected. Now, if you have a system, let's say the gas that comes in here, there is no inlet or outlet, and the gas that comes, the mass of gas that goes from here, the mass of gas, the mass M1 is equal to mass M2. So the mass of gas that comes in here is the same gas that goes out here. So M1 is equal to what? M2. Now, you know, mass, density is the same thing as mass all over volume. And if you say this is mass that comes in here and mass that goes here, so the same thing, if you integrate this mass M1 equal to M2, you have M dot 1 equal to M dot 2 with respect to time. So that means the flow rate is also equal. Now, the mass, if you check at mass now, you look at mass is, from this formula implies that mass is M1 is the same thing as the density. The density of that is density times volume. Now, and the mass at this point, the mass flow rate at this point will be the density times the volume flow rate. And the volume flow rate is this, it's expressed like this as Q, which is this. So that means, because if you check now, the density here at this point does not change. What changes here is the volume, the flow rate that changes here. So if you integrate this, what you only integrate is this. So this is like constant at that point. The density is constant at that point. So this is what we get. So now that means, since the mass flow rate at section 1 is equal to the mass flow rate at section 2, it now implies that density at section 1 times the mass flow rate at section 1 is equal to density at section 2 times the mass flow rate at section 2. So this is the law of conservation. So we're going to be using this law and the real gas equation law. So now let's go to the next page. So we now need to, now we have gotten the density 1 equal to the density 2 times the flow rate. So now the density 1 times the density times the flow rate 1 is equal to density 2 times the flow rate 2. So now what we're saying in essence, the condition at section 1, the product of the density and the flow rate at section 1 is equal to the product of the density and the flow rate at section 2. Now, when you check what was given, is a standard condition. So the flow rate is a standard condition. So now we're going to, if we want to find the flow rate at this, at any of these conditions, we relate it with the flow rate at the standard condition. Now, you see the flow rate, this means that the flow rate at any condition along the path, or any condition along that path, is just the same like this according to the law of conservation. So now that means if you have density, the product of density and the flow rate at section 1, which is the inlet, is equal to the product of density and flow rates at the standard condition. Now we are looking for the velocity. Now the velocity is here. Now that means Q1, if you divide both sides by density at section 1, you now have Q1 equal to Q, that is the flow rate at standard condition, times the density at the standard condition divided by the density at section 1 or inlet. Now we have gotten this equation, this condition now. Now we also note that, like the flow rate, you also know that the flow rate, now if you have a flow rate, the flow rate is the same thing as saying, now let's say you have a pipe like this. This is the area of this pipe. There is a speed here, which is U1. Now there is an area at this point. This is a kind of a cylindrical tube. That is the pipe. It has the same diameter. So the diameter here is equal to the diameter here. So that means D1 is equal to D2 is equal to D. And now what we're using here is internal diameter. Now that means the flow rate is equal to the velocity times area. And we're looking for velocity at section 1. So velocity at section 1 will now be equal to the flow rate at section 1 divided by the area at section 1. And since the areas are the same, since the diameters are the same, and area is equal to pi d square all over 4. So since the whole areas are the same, that means since the diameters are the same, so the area 1 is equal to area 2 equal to A. So because what the variable here is D, and since D is constant, it's the same for all of them. So that means the areas are all the same. The cross-sectional areas are the same. So that is what we're going to use. So now that means you have Q1 all over pi d square all over 4. So this is equal to 4 Q1 all over pi d square. So that means the velocity here should be 4 Q1 all over pi d square. So now using this expression here, we have the velocity to be like this. Now let's now go further. Velocity equal to 4 q all over pi d square. Now, if you check, the unit of this flow rate is what is in standard cubic feet per day, while for the diameter is in inches, so we just say inch square since it's this square. Now, the unit here for the velocity is meant to be feet per second. So now we need to get a conversion factor that will relate this velocity, which is in feet per second, to q, which is standard cubic feet per day, all over this diameter, which is in inches. So now what we're going to do now, this is, now we will now say to convert this inches square, you say 12 inch divided by 1 feet. Now 12 inch is equivalent to 1 feet. So now square, that is how we're going to do it. So now then this is standard cubic feet per day. So now this cubic feet, we're going to leave it the way it is. Now we no need to change day. So this is per day. So per day is down here. So that means we say 1 day is equivalent to what? 24 hours. 24 hours. Now we need to change this to minutes. So we have changed 1 day to 24 hours. So now we also need to change it to minutes now. We know that 60 minutes, sorry, 1 hour, 1 hour is equal to 60 minutes. Now we also need to change it to seconds. Now we know that 1 minute is equal to 60 seconds. So we have changed the whole of this. Now you see, this day will cancel out this day, this hour will cancel out this hour, this minute will cancel out this minute here. We're left with seconds here. This inch square will cancel out this inch here, inch square here. Then this is feet square. Feet square will cancel out. This is cubic feet, so to cancel out. So now we are left with, okay, this will not cancel out first because this is still in standard. So now we assume this is in, we assume this is in cubic feet. We have not done the standard conversion. So now this is in cubic feet. So this will cancel out this. So now you have 4. So 4q divided by pi d square times this 12 square will now give you 144 times this is 1 times 1 times 1 divided by 24 times 60 times 60 will give you 3600 seconds. Now we have this. So using our calculator to calculate this, we have 0.2122 q divided by d square. Let me check. Let me use calculator to check. So 4 times 144 times 1 divided by 24 divided by 8600, then divide by pi is equal to, okay, I didn't get it, it's 0.0. So So this the speed is now 0.002122 q divided by d square. So where u1 is is a gas velocity in feet per second, while q is the cubic feet per day. That is the flow rate. This is not a standard cubicle. Then d is internal diameter in inches. So this is the way to be. So this is USC is units. So now, so I haven't gotten this. So this is in cubic feet. But you know what we're given Q in standard cubic feet per day. So for us to get this, we now have to imply this equation here. I have to apply this equation to get Q1. So Q1 is equal to Q at standard condition times the density at standard condition divided by density at inlet. Now let's apply real gas equation here now. Now applying real gas equation, you know that the product of pressure and volume is equal to M R Z times T. So I can just say Zn RT Zn RT. And we know that number of mole is equal to mass over molar weight. Now let's come down to this. Now we have the product of pressure and volume equal to the compressibility factor times mass divided by molar weight of gas times RT. Now we know that density is equal to mass over volume. Now using this expression here, now from this equation up here, we divide both sides by V. You have P equal to Z RT divided by the molecular weight times mass all over V. So this is density of the gas. So now, since this is the expression for density, so now we have pressure equal to ZRT divided by the molecular weight of the gas times density. It now implies that density is equal to pressure times the molecular weight of gas divided by ZRT. Now we also know that gas gravity is equal to the molecular weight of the gas divided by the molecular weight of air. Now, and the molecular weight of air is equal to 29. Now, that means the molecular weight of gas is equal to 29 times what? Gas gravity. Now, substituting this equation into this equation here, you now have density to be equal to 29 times Pg divided by ZRT. Now we have gotten this expression. Now that means at the standard condition, the density at the standard condition will be 29. Pressure at the standard condition times the gas gravity. The gas gravity condition does not affect it, it's the same. Provided there is no external component added to the gas, so it will just remain the same the way it is at any condition. So now then the compressibility factor changes with conditions. So the compressibility factor at the standard condition, which is ZB, then our gas constant is constant. Then the temperature changes with condition too. So that is what we have here now. Now, the compressibility factor at standard condition is equal to 1. So that means the gas density at standard condition will now be equal to 29 times base pressure times gas gravity divided by RT. So we have this. Now, at any other condition, density at the inlet will now be equal to 29 Pg all over Z1 RT1. Now we have gotten the density at the standard condition, which is 29 Pbg divided by RTP. So now the density, the inverse of density is the same thing as Z1 RT1 all over 29 P1G. Now the density divided by density at the standard condition divided by density at the inlet condition will now be equal. It's something as saying the density at the standard condition times the inverse of the density at the inlet condition, which is equal to 29 Pbg all over RTV times Z1 RT1 all over 29 P1G. So see, this is the inverse of P1, which is the inverse of density at the inlet, which is this. So now that is what I used here. Now we're going to cancel the constants. We remove the constants. This one will cancel out. This constant will cancel out. This 29 will cancel out because are constant. So now we are now left with, that means the density at the standard condition divided by the density at the inlet is equal to the pressure at the standard condition divided by the temperature at the standard condition times the temperature at the inlet condition divided by the temperature, the pressure at the inlet condition. So now this is what we get times, this is Z1. Z1 is still there. This is Z1 here. These are the things that are still remaining. Make sure we pick them. So we have Z1 T1 divided by P1. So now we have this to be equal to this. Now we recall that we said that Q1 is equal to this. So the flow rate at the inlet condition is equal to the flow rate at the standard condition times the density at the standard condition divided by the density at the inlet condition. Now we have gotten this, which is this. We now need to substitute it here. So now we'll have the density at the flow rate at the standard condition times this. So now we have PB all over TB times Z1 T1 all over P1. So this is Q1. And we also know that this velocity is equal to the velocity at the inlet is equal to 0.002122 Q1 all over d square. So if we replace this Q1 here with this whole thing, you have 0.002122 times Q B all over d square times BB all over TB times Z1 Z1T1 all over P1. So that is it. So now that means we're going to use, now recalling what is B1, which is 160 times 10 raised to the power 6 standard cubic feet per day. We also know our PB to be 14.7 psia. We know our TB to be 520 degree Fahrenheit, our T1 to be the same thing, 520 degree Fahrenheit. We also know our P1 to be equal to 1200 psig. So to change this psig to absolute, we add the standard pressure, or we say we add the base pressure. We add base pressure to 1200, you have 1214.7 psi. So that is what we're going to use here. So now for P2, which is 700 psi g, is the same thing as 714.7 psi a. Just added the base pressure. So now that means the velocity at the inlet will now be 0.002122 times 16 times 10 raised to the power 6 times the base pressure is 14.7 divided by the temperature, which is 520 times all of this divided by d square. So this divided by, this is P, B, we've done that, which is this. Now we have Z, which is 0.95 times T1, which is 520, divided by P1, which is 1214.7 psia. So, and we have not gotten our D. D is the outer diameter minus 2 times T. You know, if you have a circle like this, the outer diameter, the inner diameter, when you check, there is thickness here, thickness here. So this D here the outer D is equal to that D plus 2T. So that means D is equal to the outer D minus 2T. So that is why it's like this. So 18 minus 2 times 0.375. So you now have, what we have now, what we have, we say 18 minus, see 2 times this will give me 0.75. So if you say 18 minus that will give you 17.25 in inches. So let me check with calculator. So 18 minus 2 times 0.375. So that is it. So that means the outer diameter is it. So now the velocity at the inlet will now be 0.002122 times 16 times 10 raised to, this is okay, 160 times 10 raised to plus 6 divided by d, which is d square, which is 17.25 square, times this is 14.7 divided by 520 times 0.95 times 0. Times 520 divided by 1214.7 psi. Okay. Now let's calculate. Let's run the calculation. We have 0.002122 times 16 times 10 raised to power 6 times, now here this is the same, it will cancel out, so it will be times 14.7 times 0.95 divided by 1214.7, then divide by 17.25 square equal to, so as the speed is 13.12 feet per second. Now, so to get the velocity at the outlet velocity, when you check out this formula, velocity you want to know, assuming the whole of this and this is constant, you see that the pressure, what we're going to change here, the temperature is the same because it is an isothermal process. The compressibility factor is the same. Now what changes is the pressure. We assume the compressibility factor to be the same, but which is not likely to be, but that is the assumption here. Now the only thing that varies is the pressure. So now when you look at this formula, you see that the velocity is proportional to the pressure. So since velocity is proportional to the pressure, now to get the velocity, since the velocity is inversely proportional to pressure, so now to get the outlet velocity, we just say u1 times pressure 1 divided by pressure 2. So we now have 13.12 times 1214.7 divided by 714.7. So it will now give us an outlet velocity of, let's say this is 1214.7 divided by 714.7. So it will give us 22. To give us 22.29 feet per second. So this is the velocity at the outlet, and this is the velocity. This is the velocity at inlet, and this is the velocity at outlet. Now we are asked to calculate the length of the pipe segment. Now for us to calculate the length of the pipe segment, we are going to use Waymouth equation. Now assuming E, which is the pipeline efficiency, to be 0.95. So what we're going to get now, we're going to use this formula: flow rate equal to 433.5 times E, which is pipeline efficiency, times the ratio of T, the base temperature all over the base pressure, times P1 square minus P2 square divided by gas gravity times the temperature of the gas times the length of the pipe times the compressibility factor, all raised to power 0.5 times D raised to power 2.667. So to solve for this L square, to solve for the L, now to make L the subject of formula, what we're going to do is we're going to say L raised to power 0.5 is equal to 433.5 E divided by Q times base temperature divided by base pressure times P square, P1 square minus P2 square divided by G TF Z, all raised to power 0.5 times D raised to power 2.667. So that means let's now to get the L now, it will now be squaring both sides. If you square both sides, that is L. So now to square both sides, that means I will just use something like this. Squaring both sides, I now have my L of this equation. I have 433.5 E divided by Q times the ratio of the base pressure, base temperature over base pressure, times P square minus P1 square P2 square all over GTF Z all raised to power 0.5 times D raised to power 2.667 all raised to power 2. So we now have our L to be bracket, we have 433.5 times E 0.95 divided by Q, which is 160 times 10 raised to power 6 times um, T, which is 520 divided by that is base temperature divided by base pressure, which is 40.7 times P1, which is 1214.7 square minus 714.7 square, all divided by gas gravity, which is 0.6 times the temperature of the gas, which is 520 times compressibility, which is 0.95 times D, which is 17.25 raised to power 2.667, all raised to power square. So let's now check. Let's now calculate for, and the length is in mile. What we're going to calculate should be in miles. So that means we have 433.5 times. So this 0. Okay, no. This raised to power 0.5. So okay, now let's use calculator to calculate this now. What we got calculating, we now have the length to be 106.7 miles, be the length of the pipe. So thank you for watching. Have a nice day. Remember to subscribe to my channel and hit the notification bell so that each time I make new video you'll be the first to watch. Thank you and God bless.